Now, I'm sure you don't want to be just an average researcher. You would like to be a research superstar. So in this last video in this section, I'm going to talk about what it means to be one of those rare, super productive researchers. How you get there. Now, there have been a lot of studies over the years about the distribution of productivity of researchers. So is there such a thing as an average researcher? And most people are fairly close to that. So if you pile up more researchers, it's all the same. Or is most of the research done by a small number of super researchers? And this has been investigated over many years in many different ways. And it turns out that most of the research output comes from a very small fraction of the researchers who seem to be super productive. So this is a graph from a paper put out many years ago by William Shockley, who was the inventor of the silicon chip, a very obnoxious person by all accounts. And he was interested in looking at whether a few people did most of the research. And what he did is he looked at a whole bunch of researchers in semiconductor research at Bell Labs, where he was director at the time. And he looked at how many citations they got, which is they published the papers, and how many other people cited the papers, which is a measure not just of whether you publish, but whether what you publish is actually any good, whether anybody else actually cared or used it. So it's a commonly used metric for how much research impact you have. Nowadays it's very heavily gamed, but anyway, that's the basic idea. And what he found was basically a power law distribution, that most people got very few citations. It's the same, most papers aren't cited by anybody or read by anybody, and then you get a power law system. It's not a Gaussian distribution with people in the middle. Most people are at zero, and then there's a tail running all the way down to very large numbers of citations. So there's a small number of incredibly productive people who produced huge numbers of citations, and most people produced very little. So the whole concept of there being an average, like a normal distribution where there's the average scientist who might have like 100 citations and most people are going to be within 50 and 150, that's not the case. Most people are, by whatever metric you use, very unproductive, and there's a small number of unbelievably productive people with huge numbers of citations. After seeing this graph, I had to go out and look up my citation stats. I'm currently sitting at about 4,000 citations, so I'm actually in the top very small fraction here in terms of citations, which is nice to know. These are what are called fat-tailed or power law distributions. These are ones where instead of being an average productivity drops off, the number drops off as the productivity goes up, but there's a tail of unbelievably productive people. And this actually occurs in many fields of life, not just research. So here we've got books published, wins in Formula One racing, how much you contribute to Linux software, winning golf, how many inventions you patent, research papers, tender single wins, Wikipedia edits, all sorts of things where you can measure the productivity in some sense, like how many races you win, how many papers you publish. And in almost all cases, you see the similar curves. These have all been shifted sideways by various amounts, so they're not all on top of each other. But you see that the most common value of productivity is close to zero. And then as you get more and more productive, the numbers go down and they drop fast. But there are still some people, this is a log scale. So whatever these stars are, let's see, that's don't know what that is. Research papers, okay, so most common number of research papers is zero, but there are some that publish hundreds of research papers. Very few people, most publish almost zero. Likewise on this one, most people are here, but there's a small number with much higher values. In fact, it's almost a fairly uniform curve. Some are straight, some are curved, but at the steep end, it all seems to be a steep drop, but not steep enough. This curve doesn't converge. That in fact, the bulk of the work is done by a small number of mega productive people down at one end of the tail. There's even a law for this, it's called Price's law. What it says is if you've got an organization which contains n people, half the work is done by root n. So if it's a small company with 4 people, that tells you that half the work is done by root 4, 2, which is what you'd expect. If you've got 10 people, half the work is done by 3 of them, because those 3 are presumably more productive or more motivated than the rest. Now if you've got 100 people, square root of 100 is 10, so it's saying that half the work of the whole 100 is done by 10 people. And if you're up to like 1,000 people, it's 30 people are doing half the work and the other 970 are doing the other half. This is partially a joke, I think, but it's quite true for many organisations. I remember someone showing me an organisation chart for NASA, and it had all the managers and the deputy managers and the deputy managers all the way down to all the people who did the work. And he said the secret to understanding NASA was to turn it upside down. That there's usually a small number of people, often in very junior positions, who do almost all the work, and then huge numbers of parasites at the higher level who live off their work. And the trick to getting anything done, he said, was to find who that small number of people were and go and talk to them directly and just bypass all the layers of administrators and bloat and so on. And this is how some companies deliberately design things. I know companies like SpaceX, Tesla, Elon Musk is famous for saying that you need to find the absolute best people and work them to the ground. You don't solve problems by stacking up more staff. You solve problems by stacking up that small number of super productive staff and forgetting about the rest. But this begs a question, why? And there are at least 3 different theories for why a small number of people produce huge amounts of productivity, as measured by this, which may or may not be accurate, and most do not. So probably the naive thing most people immediately jump to is the idea that there are just a certain number of absolute geniuses out there, mega brilliant people, and huge IQs or whatever other characteristics they need to be extremely productive. And so what these people would say is, if you're a manager or a government, you need to go and find these people and employ them, and then everything will be wonderful. So that's one extreme point of view, that there are a certain number of, this would be the definition of a genius, someone who's way down the tail of this distribution. And a genius is an amazing person who would be incredibly productive, and just find them. I don't know how you could increase the supply of geniuses. I suppose lots of geniuses die young or end up in dead-end jobs. So the whole secret would be identifying these people and putting them in the position where they can do the most good. But an opposite theory would be that this power law tail is due to feedback loops. The idea might be, let's say you've got 100 researchers and they're all equally brilliant, and they start on their first postdoc and they do their first bit of research, and just by random chance some of them will discover something interesting and exciting and some won't. I mean, research is always a semi-random process. That's the whole point of research. If you knew what you were going to find out, there'd be no point in doing it. So maybe some people do extremely well, not because they're any smarter, but just because of sheer blind luck, and other people don't do so well, again, not because they're stupid, but just because of sheer blind luck. But the people who do well, they get high impact papers, give good talks, which means that they get that next job. Whereas the people who just randomly, not because they're stupid, didn't do so well, don't get the next job, and so they drop out of the astronomy pool and go and do something else, which might actually be a better thing. But they're no longer in the statistics. They might be saving climate change or educating or something else very important. But if we're again looking at the stats of people who stay in science and stay publishing papers, the people who got that first break of luck get the next job. And because they get the next job, they've got more track record, they've got more citations, they've got more publications. That's going to make it easier for them to get grants. Because when you apply for grant, people look at your track record, say, this is a productive person, they've done all these wonderful things. Because they've got grants, they can hire more people, they can get more equipment, so they can do more experiments. They became better known, and therefore people read their papers because they say, oh, it's the latest paper from Brian Schmidt, I'm going to read that one. Whereas a paper from someone maybe equally brilliant who no one's heard of, they just go in the pile of unread papers. And so there's a feedback loop where those who do well, maybe purely for random reasons at the front, get more chances to do better. They get more money, they get more positions, they get more jobs, they get more freedom, people read their papers. And so this could be why you get a small number of people with huge amounts of impact, not because they're geniuses, but simply because of positive feedback loops. And there's a third theory, which is actually the one that Shockley originally came up with from that graph. His idea was that to be a productive anything really, but let's say researcher, it isn't just one skill, it's a whole bunch of different skills which he thought might not be well correlated with each other. So for example, you have to be good good at coming up with ideas, which might involve networking skills, creativity, a streak of independence. Then you've got to be a good experimenter, so you've got to have good manual skills to make the experimental equipment work well. You've got to be precise. You've got to be able to know when to stop and publish. You've got to be a good communicator. You've got to be able to write things up. You've got to be able to apply for grants. And let's imagine there's like 10 skills, and to be a mega productive researcher you have to have all 10 of them, but they're all random. So in this case, let's say there's a 50-50 chance of you having any one of these skills. Most people on average might have 5 of these skills. Some might have 7, some might have 3. Very, very few will have all 10. But 9 will be more common. And it turns out this sort of model, where there's a whole bunch of skills, each with a certain probability of having them, tends to give you the sort of power law curve that we see here at the top end. It's just because all these skills have to align to make the mega productive researcher, and that's just a rare thing. So I think that probably counts as something like some people are just brilliant, but it's not actually they're just brilliant. The people who aren't mega productive people probably have 80% of the same skills. It's just that the difference between having 10 skills as opposed to 8 in this list is the difference between publishing 1,000 papers and publishing 10 papers. So which of these is true? I mean, that's still up for very much to debate. I think there's probably some truth in all these different possibilities.